Right, Jeff. Series harmonic resonance. So, what we're going to do is look at how resonance in harmonic can be a bit of an issue, right, in terms of the components of the circuit. Series resonance, you may or may not remember this term from earlier studies, right? But series resonance, well, resonance is a point in a series circuit where omega times L, omega being the angular frequency of a waveform, is equal to 1 over omega C. And that's where omega is equal to 2 pi f, the frequency in hertz. I.e., it's where the capacitive and the inductive reactances are equal in magnitude, which produces the following impedance phasor. So, effectively, this line up here represents an XL. If that is the same length as this line here represents XT in the negative 90 position, yeah, the overall reactance is here at 0, X overall, because we use this formula. The total impedance of the circuit is R plus X, XL minus XC in brackets times J. So, if at resonance these two items are equal, that bit in the brackets there is equal to 0, and therefore the impedance is the resistance. Yep. All the other situations, remember, if we increase frequency, the blue line would get longer. So if we increased frequency up to there somewhere, all this phasor here, upwards, and increase the overall impedance. Alternatively, if the red phasor got longer than the blue one, it would pull it down that way and the impedance would be bigger. So at resonance, the impedance of the series circuit is at its lowest value. It's equal to the resistance, and that's the lowest it can be because the resistance doesn't change with frequency. You all okay with that? Yeah? So, the occurrence of resonance with unintentional harmonic frequencies. So you can get this situations where what's called non-linear devices in electronic circuits cause harmonic frequencies to be superimposed onto your main sine wave in an unintentional way. So if they didn't filter the output of inverters carefully, then they can have the effect of causing unwanted harmonics on the supply, which is an issue. I'm going to show you why you don't want that. Yeah. So if we have resonance with unintentional harmonic frequencies, has the potential for significant problems in power circuits, as the following example will demonstrate. So we got this circuit here. It's a series RLC circuit, 2 ohms of resistance, 500 millihenries of inductance, 0.2 of microfarads of capacitance. We're going to apply to that a sine wave of 600 sine 335 pi t and a harmonic, which is the third harmonic, because 1005 is 3 times 335. Right, and we'll show that what happens when we get resonance with this third harmonic as compared to what we would consider to be the intentional design of us going to be supplied with 600 sine 335, the fundamental. Yep. Note, we'll make a note that to all intents and purposes the angles of the voltages at each of these components magnitude that we're interested in. We're going to include the angles in our calculations at times, but they aren't the most important thing. That's how many volts it is, the issue, not how much current is flowing. Alright? Remember from our previous studies that we can consider the fundamental and the third harmonic separately, right? And the total current and everything would be those two added together. Right? So we'll start by considering that's equal to omega L, which in this case, omega's, will you tell me what omega is? No, taken from the specification. Remember the specification of sine wave? The 600 is the amplitude. T is time. And omega inside the sine function. So what's omega worth there? 335 pi. Inductance is 500 millihenries, right? Yeah, half a Henry. Right, I make that 526. 0.2 yeah. So that's the inductive reactance. The capacitive reactance at the fundamental. 1 over omega C. That's 1 over 335 pi times 0.2 times 10 to the minus 6. And I make that 4751 joules. Please just check them because I have been known to get them wrong. Therefore, Z1 that's equal to R plus XL minus XC times J, which is resistance to 2 plus 5 minus 47.1. That. So, operators, because you all remember how to do that. Please just check these calculations. And 4225 ohms angle radians 1.57 right. Check the impedance due to at the fundamental frequency. Yeah. So now we can calculate the fundamental current I1. That is the fundamental voltage 600. No angle specified, so we assume it's nothing. Right. Divided by this impedance 4225 angle minus 1.57 radians. The answer to that is 0.142 amps angle 1.57. You know how we do that? We divide 4225 into 600. We subtract minus 1.57 from 0. So it changes the sign. Yeah? Peter, you're looking puzzled. Yeah? So that's the current due to the fundamental 600 volts. Yeah? Then we can find VC at the fundamental, VC1 I've called it. That's the 4751. Not worried about the angle. That's the XC. Let's just write that down there. XC times I1, which is 4751 times 0.142 equals 675 volts. If we were interested in it, you'd include the angle of the impedance. But for a capacitance as minus 90. In this particular problem, we're not worried about it. All right? And VL1 is XL times I1, which was 526.4.2, sorry, times 0.142 equals 74.7 volts. In this particular problem, yes, these are at different phase angles. Yep, these two voltages. But in this instance, that's the magnitude we're interested in. Yep. If we were interested in the angle, we'd have to have XC at minus 90 degrees. We'd have XL at plus 90 degrees. We'd have to include that 1.57 radians in the current as well. All right. So that's the situation in terms of the intention design of this circuit. Is that it's supposed to carry a current of 0.142 amps, all right, and the capacitor needs to handle 675 volts, and the inductor needs to handle 74.7 volts. All right. So, over the page, your job now is to do the same calculations first of all, determine if the circuit is resonant at omega 3. So if you find, what you should do there is find, again, start off by finding XL3 and XC3, and are they equal? Yep. And then if they are, your impedance is equal to R, and then you can go on and do the calculations to find the current flowing and the voltage across the capacitor and inductor at resonance. Everyone know what to do, or do you want to do it together? Right. So how do I calculate XL3 then? Yeah, so it's omega 3 times L. That comes out, I made it 1578 for significant figures. Ohms, we should have in there. And then XC3. Times C. So that's 1 over 1005 pi times 0.2 times 10 to the minus 6. And I got 1584. So to three significant figures, they are the same, aren't they? Yeah. We round those 2 to 3 significant figures. No, not quite. But they're near enough for us to say that circuit is resonant at the third harmonic frequency. Yeah. So I'm going to make a statement to that effect here. Therefore, Z3 is equal to R is equal to 2 ohms. We'll understand why that happens, because those two reactive components cancel each other out. Yep. Therefore, I3 is equal to V3 over R. That is 20 volts over 2 ohms equals 10 amps. Right. So where in the at fundamental the current was 0.142, only a little over a tenth of an amp. Here we've got 10 amps flowing due to 20 volts being applied as opposed to 600. Yep. This means VL3 we can say that's equal to VC3 because they're both of the same impedance. They just got completely different angles. But because we've made the assumption that the capacitive and inductive, capacitive inductive reactance is equal at resonance, so we've only got one voltage calculation to do. I've taken the 1578 as being close enough times the 10 amps equals 15,780 volts, or 15.7.8 kilovolts. 3 exclamation marks. Will fry you. Not really a good idea. Someone want to kill themselves. Well, the amps will depend on their body resistance at the time. Well, considering you need 50 milliamps to kill you, somewhere around about 50 milliamps, 52 milliamps is enough to stop your heart. Not a good idea. So, in summary on the next slide, right, so we had, from the first calculations, we had 0.142 of an amp, a 675 volts capacitor, 74.7 inductor. Here we've got 10 amps flowing, harmonic, right, and we've got 15, nearly 16 are two reactive to proton. Alright, now these calculations demonstrate a 70 times increase in the current flowing to the third fundamental, which is the intended applied voltage. Okay. There's also 212 times increase in the inductor voltage and 23 times increase in the capacitor voltage. What do you think the implications of this for the circuit and its components? Notwithstanding that there's 15 kilovolts sitting there for someone to put their finger on. Kilovolts to see the capacitor of the voltage. kV possible insulation breakdown. It was designed for 600 volts, and you go and apply 15,000. You know, it's a possibility. 10 amps likely to be significantly more than the current rate. Of the inductance winder. Certainly, if you're only expecting circa 0.2 of an amp to flow, are you going to put in conductors that are going to be capable of taking 10 amps? Probably not. Yeah? So it's a situation that we want to avoid. Alright? In your notes, there is another question there for you to have a go at. An inductor has a maximum current rating of 2 amps, a resistance of 14 ohms, and an inductance value of 670 milliamps. If this inductor is connected in series with a 1.68 microfarad capacitor with a working voltage of 120 volts, 25 volts, show that it would be okay to apply 60 volts at 50 hertz, i.e. when omega is equal to 100 pi, but not to apply 60 volts at the third harmonic, i.e. 150 hertz, or omega is equal to 300 pi. Yeah. So you're going to do the calculations for 50 hertz and show that that would fall within the rating of the capacitor and the inductor, and then do the calculations for omega is equal to 300 pi. Pretty sure you're going to find that's resonant, and that it won't come within the 2 amp 125 volt working voltage of the capacitor. Right, over to you.